already understood what the earthquake is for the commercial and residential building design as per the IS code of earthquake forces. Today we applied the same code 1893 of the earthquake forces, earthquake design to the gravity dams. It's simple to understand. Many times we create things complicated. So before going into complication of earthquake, let's simplify things. That how the forces would be exerted by the earthquake. Forces generated, exerted on the structure, and today's structure is dam, gravity dam, on which the earthquake is going to give its impact. So let us begin with that. The earthquake mostly create the waves in the crust, the earth crust, and those waves exert the forces or exert the pressure onto different parts of the dam. So where the dam is, what happens that the earthquake waves which passes through the foundation of such location where the gravity dam is located, they may be in any direction, x, y, z. If you resolve the forces or the pressure being exerted into 3 dimensions as per the geometry of the gravity dam, then if we assume that along the axis of gravity dam is x-axis, perpendicular to it is y-axis, and vertical direction is z-axis, then you would be comfortable to understand that along the axis, that is x direction, there won't be any much movement, because on both sides of the gravity dam would be like hills abutment where the pressure or force would be transferred directly, and gravity dams doesn't fall because of the forces in the x direction on or along the axis of the dam. Mostly the failure is because of the horizontal forces of water, and that is the y direction of the earthquake waves. So when earthquake waves are causing pressure or force in y direction, that is the perpendicular to the axis of them, then it is a major concern to calculate the different forces. The third direction is z direction. Z direction is vertical direction and is also important because we consider the load, weight of the dam, self weight of the dam in vertical direction, and it is a stabilizing force. It create the overall stability of the dam. When there is a Z component in the earthquake waves, then we need to also mention and look into that it is going to give a kind of impact to the already calculated forces onto the dam. So now I think the thing is clear that the forces which are perpendicular to the axis of the dam are more detrimental. If we divide the forces, the forces from the earthquake are not going to be in one unique direction. They are perpendicular or oblique or something, but we could divide all them into 3 categories. That is along the axis, perpendicular to the axis of the dam, and vertically down or upward to the axis of dam. One more thing I want to mention here, that the earthquake waves may bring, like sometimes in the direction of forces, like in the direction vertical, if I consider vertical movement of the dam, then it may add to the weight or it may reduce the weight depending upon the positive or negative side the wave are exerting. Basically, it is a vibratory force, and we have to take the worst combination when it is reducing the weight, because when it is increasing the weight of the dam, then it is not detrimental to the structure and analysis. So what we do when it is reducing the weight of the dam, so that becomes the detrimental. And when it is perpendicular to the axis of the dam, and when it adding to the hydrostatic force acting upon the dam, then it becomes detrimental. One more important thing in the earthquake forces I want to mention is that earthquake waves mostly they create acceleration in the foundation, not in the dam body. You take this statement in your mind. This is consideration in the IS code 1893 of the earthquake forces and design that the waves, earthquake waves, generally generate acceleration in the foundation in even residential analysis or commercial analysis, high rise analysis of the earthquake forces. That foundation is basically accelerated because of the earthquake. So there are three four things which are important because of the earthquake. Is first is the magnitude amount of the earthquake. Say onto the Richter scale, it is 5, 6, 7, 8, depending upon its how far it is. The second point is that this epicenter of this earthquake is from your structure, gravity dam, how far it is, say 100 kilometer, 200 kilometers. So severity will definitely reduce. And also the depth at which it is acting. Suppose depth is 1 kilometer, 5 kilometers, or say 20 kilometers. So that, yes. So that affect the severity of the earthquake forces. And the last is the important factor, which is because we consider also the response spectrum of the structure in buildings as well as in the gravity dams. So what is the the time period of vibration of the building or the gravity dam? So in the response spectrum method, we consider that. Now, what is important here is that in the first slide we have seen things which are there, that it sets the acceleration into the foundation, and when foundation moves, then what is the response of the gravity dam? That it will give the inertia resistance in form of inertia force. So structure want to be stationary, but the foundation is moving. So the force is always against the acceleration of the foundation. So whenever there is a say acceleration in upstream side of the dam of the foundation, then inertia of the dam body would be onto the downstream side. When the inertia is onto the inertia force into onto the downstream side, means it is adding up to the hydrostatic force. So when it is adding up to the hydrostatic force, means that is the worst combination. If it is reducing the hydrostatic force, then it is a favorable condition which we are least bothered about. We are seeking the worst combination in that case. There are certain things here mentioned that the response of the structure to the ground vibration is a function of nature of foundation, soil, material, form, size, and mode of construction, structure, duration. These are from the IS code, intensity of ground motion. Earthquake causes impulsive ground motion, which is complex, irregular in character, changing period and amplitude. Earthquake is not likely to occur. These are the IS code provisions. Just I'm narrating because earthquake is not likely to occur simultaneously with wind or maximum flood when we are combining these forces. So earthquake we do not consider. The value of elastic modulus of elasticity can be taken for the hydrodynamic analysis also. And the compressive, the last bullet says that the compressive permissible stresses could be increased by 1/3, as you might have seen it in the earlier subject also, by 1/3 when we are considering the earthquake forces. So that is important. You should not forget to increase the permissible stresses, because if you design it with the permissible stresses for the normal structure without considering the earthquake forces, so when you are considering earthquake forces, you should enhance, increase the permissible stresses of IS code 456 by 1/3, so that your design remain economical. If you forget this one small thing, then the design would go very much uneconomical. You might have seen this from the IS code 1893 1984, and there are many revisions of this earthquake forces, especially after 2002. Yeah, the whole this area, the zone 1 has been removed, and all the area is now starting with zone 2 and so on. But this sketch or the picture carries all zone 1 to the 5 being severest. So that is what. Now the IS code defines in terms of gravity dam that we could design the dams in two categories, one below the 100-meter and one those which are higher than the 100-meter. So there are two methods adopted. One is the seismic coefficient method, and second is the response spectra method. So what is difference between two is that the seismic coefficient method of 1893 for gravity dam, that it doesn't take the response of the structure into consideration. So it's a very lesser demanding, challenging method of design through considering the earthquake forces as compared to the response spectra of the structure, if we consider that. So in that case, we have to also calculate the T, that is the period of this structure. So there are two methods. So here I would like to again mention that in both methods, we are mostly interested in the horizontal coefficient of acceleration being imparted to the foundation, which would be detrimental to the design. So I'm taking you to the next slide and would explain how it affects. This is very important slide to understand that how the earthquake force is really important. So in both, in case of first, the seismic coefficient method, and the second is the response spectrum method, both the formula are written that what we are calculating alpha h, what the alpha h is, that the horizontal seismic coefficient. This is not acceleration, but it is a coefficient which we are which is going to be very important in all the calculation, whether they are horizontal forces. This is not force. This is a coefficient which the amount of force getting onto the structure, dam structure upstream or downstream, on the top or bottom of the dam. That will see that how it the alpha h would be important in terms of calculation of the forces, earthquake forces. So here you could see that basic seismic coefficient, the alpha h for seismic coefficient method. First, I'm looking at that is the beta I alpha 0, where alpha 0 on the top of this bullet 1, you could see that basic seismic coefficient alpha 0. This is from the IS code 1893. Directly we can take the values depending upon, I show you in the next slide how the alpha 0 is calculated here. That alpha 0, the values are given, you could see here in your mobile, that alpha 0 and f0, that is the first this slide alpha h we are calculating for the first method, that is the seismic coefficient method. The value of alpha 0 is taken from this particular table from the IS code, and the values you could see here, that these are the different zones of seismic zones 5, 4, 3, and 2, and these are the values of alpha 0, 0.08, 0.05, 0.04, and upon the severity of the zone, they are taken into consideration while designing the structure. So what is this? F0 is seismic zone factor F0 in different zones shall be taken as given in the table from the IS code. The design seismic forces of the structure I and the soil foundation system beta. So let's go to I and beta so that we can understand this alpha h is equal to beta I alpha 0, and F0 is taken in the second F0 SA by G. This formula is important, very simple. we need to understand only the terminology in these two formula. Both are same. One is valid for one is valid for the structures having 100-meter height or less, and second one is for above 100-meter height of the dam gravity dams. So here we are using BIF0, and in above alpha 0 SA by G. So SA by G, we'll see how to calculate in subsequent slides. F0 seismic zone factor for the average acceleration is spectra. This is spectra means when we consider the vibrations of the structures and we calculate. So these values are mentioned here for the F0 directly from the IS code. So that can be taken, and the value of importance factor I are here mentioned, and you could see the dams of all type are taken, importance factor is 3. Rest of the structures from that same IS code 1893, they 2 or 1.5 or all other as 1. If not important, we are not going to enhance this value to calculate alpha as 0. So this I factor. Now the beta factor, the different foundation, soil and foundation system, and like you are having raft foundation, pile foundation, combined RCC foundation, and so on, and the value of beta should be selected like this. For rock or hard soil, medium soil, and soft soil, mostly this is 1, and ranging from 1 to 1.5. So for well foundation and soft soil, this is 1.5 here, and pile passing through any soil but resting onto the soil type 1. So directly to the rock or hard soil pile, if you are taking that, then your beta is 1. We are not increasing the value to 1.5. So basically it varies between 1 to 1.5. The same slide here for the alpha H, and now we are going to get the notion understanding of SA by G. The where SA by G average acceleration coefficient is read from the figure, the sketch I'll show you, that is from the again IS code. Uh, uh, the acceleration coefficient is read from the figure for a damping of 5%. Damping, I assume you people understand what is damping. When you draw a vibration graph of any structure or a spectrum of any structure, then along the time the amplitude gets damped, means keep on reducing with time, and ultimately it dies out. So maybe in say 5 minutes of time or 3 minutes of time, it lasted, suppose earthquake lasted for 2 years, so damping within 2 minutes, how much is the damping? 5% damping, 10% damping, 20% damping. So damping, if it is more, then it will last for lesser time. If it is lesser, damping is slower, then the earthquake would last for longer duration. So that is what we consider here is that for a damping of 5% for gravity dams, that is mentioned in the code. Damping of 5% and fundamental period of vibration of the dam corresponding to this formula is used. This is again, I say, very easy formula. Only the too many quantities are mentioned, but they are nothing, and these are the characteristic of them: height, base width, and the elasticity. So T is calculated based on the geometry of the, and accordingly what we go to the next slide of IS code chart given here, that along the x-axis what is natural period of vibration in second, which we have calculated from the formula given above. But we are continuing. We'll conclude on mobile only. So just be with me for 5-10 minutes more. I'll complete this. So on x-axis, you could see that there is average acceleration spectra, and onto the y-axis, what is there? SA by G, average acceleration coefficient, that to be taken up from with 4-5% of damping. So we selected that graph of 5% of damping. Here different dampings are mentioned for different structures, and we calculate only for that. So S 5% damping and mentioned, and based on that value we could calculate SA by G that need to be calculated and taken into alpha H coefficient, horizontal coefficient of acceleration. So from here we calculate SA by G and we use there in the formula. Now after calculating alpha H, what happens, how to go ahead with the calculation of force. So let's see. Effect of horizontal acceleration causes two forces, not only one. Like hydrostatic force, water which is standing against the upstream face of the gravity dam causes only hydrostatic force. But here, since there is a movement in the foundation and a horizontal force of inertia being exerted on the dam, but there is also water standing against it, and the waves would be created because of the waves in the foundation. So there are two type of forces which will get exerted because of earthquake event. One is the inertia force in the dam of the body, and second is the hydrodynamic pressure of the water which is standing against the upstream face of the gravity dam. Now, the first we take the first case of the inertia force. That inertia force acting on the dam body. So inertia force, the alpha H which we have calculated, it doesn't affect much at the base of the dam. As you could see onto the right hand side, right top corner, there is a small triangular shaped diagram mentioned here. You could see it. So this graph says that we take the coefficient C is equal to 0. On the top, it is C alpha H. This is the height of the dam which we are considering that acting upon the dam, the value of alpha H. So at the base, it is 0 and increasing to C times alpha H. And the value of C for the horizontal forces, it is 1.5, while vertical it is 0.75. So take care that alpha is same, but for the horizontal, we are considering this value of C as 1.5, and for all the vertical forces, we'll take it as 0.75. Okay, so I'm going down to the next slide so that you could understand how it is taken into consideration. Now, the value of alpha H is in the horizontal inertia force we take is 1.5. So this one for the now this inertia force, you read just this paragraph, you would understand that inertia forces acts in direction opposite to the acceleration imparted by earthquake forces and equal to the product of mass of the dam and acceleration. Very simple. That we consider the mass of the dam and acceleration, which we are calculating here. What would be the acceleration? Acceleration would be not alpha H, C times am I audible, Janam?
Yes, sir, audible now.
Okay, okay, fine. I was audible na throughout.
Yes, sir, throughout audible.
Okay, okay, fine. I'm taking you back to my slide. Okay. So this is very important explanation about the inertia force. I'm holding the slide for 30 seconds. You just read this. To downstream or downstream to upstream to get the worst combination for design. When we are designing, so we'll take the worst combination when it is inertia is increasing the hydrostatic force. So we have to add into. So horizontal force is what? Hydrostatic force is the acting upon it, and then this earthquake forces would be added to that. So reduction, we are least concerned. If it is the hydrostatic force getting reduced, it's okay. We are least concerned about. It causes an overturning moment about the horizontal section, adding to that caused by the hydrostatic force. That is what written here. So we are now here. For dam, that was for the, we are multiplying just by the that C alpha H to the weight of the dam, and we'll get the amount of earthquake force, horizontal inertia force, which is adding to the hydrostatic force. When dam is above 100 meter, the response spectrum method shall be used. It's very important how to use this. So alpha H we have calculated separately in that case by the T. So that alpha H is taken into this, and these two formulae are given 1893 for calculation of the shear force and the bending moment. And where it is calculated, because the worst combination is at the base of the dam. Overturning is basically major trouble in the gravity dams. So these are taken at the base, calculated at the base of the dam. So VB is 06 W, that is weight times alpha H. This alpha H is the second one which we have calculated using S by G value. Okay, and similarly, the value of MB, there is no need to prove these formulas because these are empirical formula and given into the IS code and can be directly understood here. So you can use even the IS code while designing the dam. So this is the shear and this is the moment because of the horizontal force exerted by the uh, earthquake waves. Okay, the bottom two equations need not to be like given much, but when you need to calculate the shear and moment at a particular section, not at the bottom, but say at 10 meters from the top or 15 meters from the top or 20 meters from the top, then we need to calculate use the equation which are mentioned at the bottom of the slide. And if we are calculating the total shear and total moments, then these are the equation because we are calculating at the base of the dam. Now this slide gives you, next slide is, because here you look at any section, the shear is CV times the VB. VB is on to top, and likewise MY is CM hyphen times MD, which is MD is given on the top. So what is CM and CV? They can be calculated from this graph, which is there in the IS code, and based on Y upon H on Y axis, you could see Y is the depth from the top and H is the total height of the dam, and value of CM and CV can be taken from this chart. So it's very simple here. Now the important thing coming, we have till now we have completed our horizontal inertia force exerted by the earthquake. Very simple. We calculate alpha H for two categories. We calculate for less than 100 meter, above 100 meter. In the less than 100 meter, we use seismic coefficient method. Above 100 meter, we use the response spectrum method, and two different formulae we have used from the IS code. That was simple inertia force. Now the hydro, I have mentioned you earlier that there is also the hydrodynamic horizontal force acting onto the dam section because of the earthquake waves. So this is how we use the Jengar's formula. Jengar formula you might have used earlier also in other equations, other applications of civil engineering. But here we are using it, the hydrodynamic forces for the gravity dam. And this Jengar's formula, you just go through very simple formula and simple way we will look at that how this help us in calculating the hydrodynamic. These are dynamic because waves are created in the water and water is exerting force onto the dam section. And this this force is not the like triangular linear force, but it is, as per Jengar, that this is a parabolic and elliptical come parabolic. This equation PEY is equal to CS alpha H gamma WH. Out of these four variables, three are known to you. Alpha H you know, gamma W is the unit weight, H is the height of the or depth of the reservoir, you could say. C is the coefficient which varies with the shape of the upstream, and that is Jengar's. Please switch off your microphone, all of you. There is noise in my ear. Okay, done. Thank you. We are going up. Now, Jengar's formula PEY, that is the intensity pressure, horizontal pressure, hydrodynamic pressure intensity is PEY, is equal to CS. CS is Jengar's coefficient, which varies with the upstream, and alpha H, gamma W, and H are very much known to you geometry from the geometry of the gravity dam. Now, this equation can be this is pressure intensity, not the total pressure. Now I am showing you the variation and the geometric variation of PEY. This is how Jengar has done that. This is elliptical cum parabolic, half parabolic, and 1/4 elliptical. So top portion you could see the variation is curved, is not triangular. In hydrostatic force, we have measured this pressure acting upon the our structured gravity dam as triangular, gamma H at the bottom, and linearly varying from top as 0 to bottom H gamma WH, if you remember that. Now here it is not the linearly varying, but it is varying elliptically or parabolically. So the diagram is like P max is somewhere down here and PEY somewhere here. And how to do the computation? We are not going to do the computation, but to find out the total hydrodynamic pressure, we have to integrate this equation of PEY, which I have shown to you earlier. So this need to be integrated in two parts. One part is the elliptical part, second part is the parabolic part. So that integration is done in the IS code, and we have been given total solution here, the total solution here, and that is what is the total formula here. The earth, the total pressure. Total pressure, you need to remember this much only, that the total pressure PEY is equal to 0.726 PEY times Y. Okay, and what is the moment? This is the moment MEY, total moment, is equal to 0.3 PEY Y square. Let's go back to that sketch, and so that we could understand other things of this sketch. 5 minutes more and I'm done. Okay. So this gives you the diagram of a gravity dam, which is having theta angle with the upstream phase. If you could look, phi is mentioned, and phi is equal to 90 minus theta, where theta is the angle the upstream phase make with the vertical. Okay, phi you could see here. This is phi, and this phi is the with the horizontal. So theta phi is equal to 90 minus theta, and theta is the angle which upstream phase of the dam. This upstream phase which makes with the. Okay, now what it mentioned that the equation we have seen the total of the total hydrodynamic force and moment about the base of the dam is that when this upstream slope is less than half the height of the dam, then we can ignore. When the upstream slope is less than the half of the height of the dam, then we can ignore the upstream slant, and we can consider is full vertical. The second, when it is above the midpoint, means when slope provided on the upstream side is more than half the height of the dam, then we consider as if the slant face is going directly, not touching here, but dotted line is shown up till the height of the depth of the water Y, or h, small h. Okay, that is what is here the IS code provision made, and accordingly this Jengar's formula is used here. That CS in Jengar's formula, I said that CS is used, that CS is the coefficient which varies with the shape, upstream shape, and how it is computed here. Empirical formula is mentioned, that Cm by 2y by h, then 2y minus h. Simple equation, empirical equation is mentioned, is long only looking just remember that this is how calculated, and the value of Cm is also given in this formula. So that is what is the thing. Cm versus the theta values are given in this, and finally the total pressure at depth y may be found by integrating any depth y you could, and it could be y could be h ultimately, by integrating the pressure curve above the plane, taking the pressure variation to be elliptical parabolic, the total pressure at depth y will be equal to the average of the areas of quarter ellipse and semi-parabola as I mentioned. So this is total, which I have already mentioned. This is very interesting. There are two more slides. Please bear with me. I just explain you. This slide is only important because when there is upstream slanting, because sometimes question asked in the your public service commission oral examination, if it is slant, upstream is slant, then what happens, that force acting is considered as acting normal to the surface. Many times when we calculate the principal stresses, then the forces are acting normal. Then if you divide the component into two parts, then there would be also horizontal component and vertical component. So this is IS code which takes into account the vertical component of hydrodynamic force when the upstream phase of the dam is slanting, not vertical purely. If it is purely vertical, then there won't be any horizontal component, vertical component, only horizontal component 100%. But if it is slanting, then there would be a component, vertical component, that need to be taken into consideration, and this is the formula. So that is how the hydrodynamic forces can be computed. And this is the vertical acceleration. In the initial explanation, in the beginning, I have explained that we need to consider x, y, z. We could resolve the all earthquake forces into three categories: x, y, z, where x is not important because it is along the axis of the dam. Y is very much crucial. Alpha h we have calculated for y component only, because there are two inertia forces and hydrodynamic forces, and the vertical, the Z component. So Z component, I have explained you that alpha H, C alpha H, the variation of this is C in that case need to be taken as 0.75 to calculate the vertical component. Vertical component calculation is not that difficult. Here, the effect of vertical acceleration means in Z direction, the effect of vertical earthquake acceleration is to change the unit weight of water. Unit weight of water won't change, but virtually it would change, and concrete and masonry. So this will give you virtual reduction in the unit weight. So acceleration upward increases the weight. Upward, acceleration upward increases because inertia would push them down. So increases the weight, and acceleration downward decreases the weight. So worst combination, when acceleration is upward, so it's in favorable condition, but when acceleration is towards the center of the earth, that is detrimental. So that is you need to consider due to vertical acceleration in vertical inertia force W, alpha V W is exerted. W is weight of the dam. So this alpha V is nothing but is equal to 0.75 times alpha H. Okay, so at this point, I stop my explanation that vertical we are considering that alpha V is equal to nothing but 0.75 alpha h. Alpha h we have seen earlier that we can calculate with two methods, seismic coefficient method and rest spectrum method, and same is taken into calculation of the total earthquake forces acting upon the dam. So with that, I conclude my presentation.